Have you ever looked at the specs for a new computer and thought, wait a minute, that gigahertz number, hasn't it been kind of the same for like a decade? We used to see it leap up every couple of years, but now it seems totally stuck. So what gives? Why did that mad dash for raw speed just stop?
I mean, this chart really tells the whole story, doesn't it? Just look at that curve. From 1990 up to about 2005, it's a rocket ship, straight up. We went from megahertz to smashing through the gigahertz barrier. The industry was in this full-on gigahertz race. And then, bam. Around 2005, the line just goes flat. For pretty much 20 years now, we've just been hovering in the same neighborhood. And that really begs the question, right? This wasn't because companies got lazy or stopped trying. Not at all. Engineers were pushing harder than ever. So why did they stop? Well, the answer isn't in a boardroom. It's in a physics textbook. Turns out they ran smack into a physical barrier, a very real limit that engineers call the power wall. And this wasn't just some small hurdle. It was a dead end that brought that whole race for pure speed to a screeching halt. See, here's the deal. You don't get more speed for free. To make all those tiny transistors on a chip switch faster and faster, you have to pump more voltage into them. But all that extra juice doesn't just create speed, it creates a ton of waste heat. And here's the kicker. It's not a simple one-to-one relationship, it's exponential. A tiny little increase in speed creates a huge spike in heat. And that is the power wall. It's the point where you're trying to squeeze out just a little more speed, but you're generating so much heat that the chip would literally cook itself to death. You'd need some absurdly complex and expensive cooling system just to keep it from melting. You've hit a thermal dead end. Game over. And for a single processor core, that number, that wall, ended up being right around 4 gigahertz. That became the practical limit. I mean, sure, you could push past it in a lab with liquid nitrogen, but for the computer sitting on your desk, no way. The industry had to find a completely different way forward. So, if you can't build taller, what do? You build wider. And that's exactly what engineers did in this absolutely brilliant pivot. The new strategy was, okay, forget trying to build one single, ridiculously fast jet engine. What if we build a bunch of smaller, more efficient engines and just have them all work together? This slide shows that trade-off perfectly. On the left, you've got the old way. One monster 4 gigahertz core. Yeah, it's fast for one thing at a time, but it runs as hot as a furnace and guzzles power. On the right, you have the new way. Multiple slower cores, say running at 2 gigahertz. Now, individually, they're not as fast, but together, they produce way less heat, use less power, and, this is key, they can get more total work done by tackling tasks in parallel. And let me tell you, this shift to multi-core processors was a full-blown revolution. Now we have computers with 4, 8, 16, or even more cores. But pay close attention to that last point. This was a fundamental trade-off. We gave up on making single tasks, what programmers call threads, run faster. Instead, we focused on making the computer an amazing multitasker. And that changed everything for software developers. But of course, there's a catch. You can't just keep throwing more and more cores at a problem and expect it to get infinitely faster. This is where a crucial concept called Amdahl's law comes into play, and it explains why adding more cores isn't the silver bullet everyone was hoping for. Okay, imagine a kitchen with 10 chefs. Those are your cores. For most of the meal prep, that 90% part of the job, they can all chop vegetables and mix ingredients at the same time. It's super efficient. But what if there's only one oven? Every single dish eventually has to wait its turn to get cooked. That one oven is the 10% sequential part of the job, and that little piece of the puzzle is the problem. That sequential part, the oven, becomes a bottleneck. It doesn't matter if you have 8 chefs or 8,000 chefs waiting around. They all have to stop and wait for that one oven to do its job. It puts a hard ceiling on how much faster you can possibly make the entire meal. And this bar chart shows Amdahl's law in action. With just a 10% sequential task, going to 4 cores gives you a great speed boost. Going to 8 gives you more, but it's not double. By the time you hit 16 cores, you're seeing some serious diminishing returns. You keep adding more and more power, but that bottleneck is holding everything back. The speed-up curve just flattens right out. So, knowing this new reality, lots of cores, but with this bottleneck problem, how did the software world respond? Well, this new hardware forced a complete ground-up rethinking of how programs are designed. Programmers had to learn how to think in parallel. So they developed all these new strategies. Think of it like being a foreman on a big construction site. You don't just have one person build the whole house, right? You break the project down into smaller jobs. Plumbing, electrical, framing. You make sure every worker has something to do so no one is just standing around idle. And you design the workflow to minimize the time they spend waiting on each other. It's a really complex, coordinated dance.
And if you want to see how this works in practice, you don't have to look any further than one of the most demanding things you can possibly run on your computer, a modern video game. A game is just a perfect example of breaking down a huge task. Instead of one core trying to do everything, the work is split. One core is dedicated just to drawing the beautiful graphics you see on screen. Another is constantly calculating the physics of the world, how things fall and explode. A third core might be busy running the artificial intelligence for all the other characters, while a fourth is doing nothing but listening for your input from the controller. All of this is happening at the exact same time, in parallel.
And this parallel thinking is absolutely everywhere now. The reason you can have 50 tabs open in your web browser without it just crashing is because each tab is running in its own little world. The massive servers that power the internet are handling thousands of us at the same time, but using these exact same principles. Parallelism is the invisible engine that runs our modern digital lives. So, this is really the key takeaway from all of this. The era of just making things faster by cranking up the gigahertz is over. The future, and honestly the present, of performance isn't about raw speed. It's about being clever, it's about coordination, about dividing up the labor, and about mastering the art of parallel execution. And this leaves us with a pretty fascinating thought to chew on. We've gone from one core to dozens in our phones and our computers. But what happens when our software has to be designed for chips with hundreds or even thousands of cores? The challenge of coordination and thinking in parallel is only going to get bigger.